these truths to be self-evident.
That all men are created equal.
As a member of Congress, I get to have a lot of really interesting people in the office. Experts on what they're talking about.
This is the podcast
For insights into the issues.
China, bioterrorism, Medicare for all. In-depth discussions.
Breaking it down into simple terms. We hold
these truths
with Dan Crenshaw.
The Eagle has landed.
All right, welcome back, everybody. We're joined today by CEO of Radiant Nuclear, Doug Bernauer. Doug, thanks for being on.
Hi.
Yeah, it'd be great to
be
have
here.
you. So, the topic of today is small modular reactors. It's become a real buzzword in the energy sector. You know, we're moving away from the common like water reactors, your big reactors that we've been building since the 60s. And there's a lot of buzz about small modular nuclear. And I think we should just start with like what the heck that even means, or maybe a little bit about your background actually and how you got here. So I mean, you weren't always in the nuclear space. What you worked with Elon, you worked at SpaceX.
Yeah, I can talk a little bit. So I'm an electrical engineer, worked at Rock Automation for a couple of years, then joined SpaceX back in 2007. So they had tried to launch two vehicles, neither of which worked yet. So it was a really tiny little company back when I joined. Was there 12 years. But while there, I worked on Mars for Elon, along with the first rocket with legs and a bunch of interesting special projects, Boring Company and Hyperloop also. And then that led me to realizing nuclear technology is required to meet that mission of making life multiplanetary, which is the reason I had joined SpaceX. And so I left in 2019 and founded Radiant to build a nuclear tech company, really. That's what it's about.
I have a random question, not to do with Radiant real quick, but since you kind of worked on those projects from the ground up, like what is it that made them successful? Like obviously Elon chooses the right engineers, but he's pretty involved as well. He's not an engineer by trade. So how does that dynamic work? It's really interesting.
Yeah. Well, I mean, Elon's a visionary. The culture of the team was built from the very beginning to be getting things done rapidly and digging in and he preaches a bunch of principles that I really believe in. Is definitely the reason I joined and fit in well. But like first principles engineering, basically to go like we're going to design something, we're going to go down to the root problem, understand exactly the physics of it and what's possible, and not just accept that this is the way it's done, essentially. So I think that process is at the root of being able to get things done. But Elon does really care about delivering something of value to society, which is really important. So not an easy win. Like he wants to tackle a really hard problem and solve it in the right kind of ultimate and final way.
He digs into the science and the technology like a lot more than your typical CEO would.
A lot more.
Yeah.
Yeah. So like the Hyperloop example is the California high-speed rail project that he read about and went, that's, we're paying a lot and not getting something with the best possible capability that engineering can provide. And so he went, what if we had evacuated tubes you could move people in? Which it's awesome to think about that idea and look at it. I mean, for Earth, it's extremely challenging because you got to keep vacuum pressure, right? But it led to a whole bunch of technology development and interest. The kind of cool thing would be, if you're on Mars and you connect cities together on Mars, you have no pressure and you automatically have Hyperloop.
That's interesting too. Yeah. Well, we got to get to Mars first. Since you worked on that, what's our biggest hindrance to getting to Mars? I've heard various answers to this.
Just leadership. Just leadership. Just making a commitment. It's money. That's all it would take
of money
to go there.
Well, there's some physical realities. I mean, I've talked to astronauts about this. I mean, have we really solved like the radioactive problem too? Just being exposed for that long, which means I guess the solution there is you have to get there quicker.
Yeah. So I actually worked on this a little bit because. So there's two things. One is you get to Mars, you have a permanent colony there. If you're going to have a person live their whole life there, you're in a potentially a higher radiation environment than you would be on Earth. But if you're under about 4 meters of Mars dirt, like you build the base, you can lay a rocket on its side.
That show,
use construction vehicles.
What was that show they did? It was cool. It was like Elon was in it. It was like a documentary, but it was not.
I don't know.
You know what I'm talking about?
No, I don't think I've seen it.
And they eventually were living underground.
Oh, you
on
definitely
Mars.
should.
Yeah, so that's the solution there.
Well, so you can do that, and you can spend about 1 hour out on the surface every day.
Yeah.
If you do that, you have about equivalent radiation dose that you get on Earth.
Okay.
And so it's kind of a solve and done problem.
Yeah.
Now on the voyage there, you could design the spacecraft so that you have like a shielded cavity, like you have water or something surrounding where you have people. You can also directionally point away from the sun.
Yeah.
because you do get some. It's not a lot of dose, but some percentage of your dose is coming from the sun, from radiation, right, from heavy charged particles from the sun.
Okay.
So you can like aim the right way on your voyage and minimize it a little bit.
Interesting. Well, thought through these things. Okay, well, let's talk about nuclear stuff. So you work on small modular reactors. So I'm going to get to like what that means technically speaking in a minute. But was this a big conversation about getting to Mars? I mean, using eventually a nuclear reactor to get there. That's not what we're using now, of course. But is that the idea one day?
Absolutely. So there's two things you can do. My focus was around having power on Mars to do fuel production, so you could refuel a Starship.
Yeah.
So I put together this study with some simulation code I wrote, and showed results to Elon and a couple of his high ups, Tom Mueller and other folks. And you need megawatts of power out into the world if you're going to do fuel production. And really, that's the thing that makes it possible to just go there and back again. It creates a frontier of civilization out into the world. But you can also use nuclear technologies to get you there a little bit faster.
Yeah.
There's really two types. There's nuclear electric propulsion or nuclear thermal propulsion. Nuclear electric propulsion, you're just making electric power, and then you use it to accelerate a noble gas out the back of a little thruster.
Yeah.
And so when you get to Mars, you could land and still use that same reactor on Mars.
Right.
So that one's kind of cool. Nuclear thermal, you can't use it on a planetary body. It's only for propulsion. You just actually heat up hydrogen and throw it through a reactor, and it goes to extremely high exhaust temperatures, so you get a high efficiency.
Yeah.
This one will get you there in 3 or 4 months, and I think this will accelerate any voyage, and you can also do both if you wanted.
Just put all the nukes on the ship.
All the nukes.
All the nukes.
Yeah.
All right. So
do all things, probably best.
So small modular reactors, again, it's a lot of buzz, but what exactly is the new technology? That's a question I've always been a little skeptical of, because every time I think of small modular reactors, my first thought is, okay, so I think we have these already. They're called they're on nuclear submarines. They've been on there for like 60, 70 years. Help me understand like what's new about the technology.
Yeah, nothing is new.
Okay, that's what I thought.
I mean, if you want to sound
commercialized,
if you want to sound really smart in nuclear without having to spend a lot of time, you can just say, if anyone asks you, has this, if they tell you this thing is new, you go, no, it isn't. We've done it before, and we did it in the 1950s or 60s in the U.S., and that'll be true for 99.9% of questions.
Mm-hmm. We did a lot in that time frame.
Yeah. I mean, we built reactors small first, and then we scaled them up to that about 1,000 megawatt, which is the size the 93 operating reactors are in the U.S. today. And now we're looking at making them smaller again, and it's because mega projects don't work anymore.
They're just too expensive.
In the U.S., we've just they all go over budget.
Let's talk about that for a second. Just what should we be doing? We did pass some good legislation this year on that front. I don't know if it's the end all be all. What should we be looking? I mean, nuclear has to be the future. There's a growing agreement on that, at least on the Republican side, and we've kind of bullied the Democrats into understanding that it needs to be true. I'm not a fan of intermittent, unreliable energy taking over more of a share on an electrical grid. It's just not a good idea. The math doesn't work. But what do we need to do different?
Yeah. Well, I think breaking the problem up into smaller pieces is helpful. There's basically grid electric power, and then there's off-grid power. And actually, what I'm working on, maybe I'll unpack that first.
Yeah.
So you've got your 1,000 megawatt reactors. That's your typical large grid scale. Really hard to finance, slow to build. Right, it takes 2 to 3 times as much money and as much time as you'd like right now. And back in the 1960s and 70s, the U.S. actually built at the faster speed, 6 years to build a reactor. That's what's normal.
Right.
As fast as it's about 5 years in China. About, I think, in 4 years for Japan is like the record. Like all their fleet was built in an average of about 4 years for these giant reactors. Small modular reactor is a lower power size, maybe around 100 megawatts. There's some up to 300. But about it's about 10 times smaller. And the idea is it's easier to finance that. It should be quicker to build it. There should be less infield welds, less of a total area needed. And that's really just the hope that we can keep the prices that you get when you have a really large reactor are the best. That's the best economics to build the 1,000 megawatt system. And so the hope for SMRs is that we can build these extremely fast and have them on the grid and make really low cost electricity. If you go 10 times smaller than that, you got a micro-reactor.
Right.
Which still is big enough that you need to dig a big hole in the ground. It's still a construction project.
Yeah.
But that can target a really small market.
Yeah.
Where it wouldn't make sense. Maybe you don't have the distribution lines to transmit 100 megawatts of power, right? And you want to localize that energy. But what I'm working on is a 1 megawatt reactor.
Yeah.
Which
So
really
how many
only
homes,
makes-
somebody was talking like powering homes, how many would that power?
Yeah, power about 1,000 homes,
Yeah.
or you can think about it as 2,000 servers, 1.8 million gallons of water desalination per day per unit, or charging electric vehicles. You
Yeah.
can do 480 of those per
Yeah.
day per unit. And what I'm working on is totally off grid. All these other reactor sizes that you could target are about low cost electricity on a grid somewhere, and we're trying to play with those metrics to make it so it's a lower cost to build it and a shorter lead time, so you can quickly turn it on.
So very much built for purpose would be a big difference, I guess, is when we're talking about SMR versus your classic big reactor. Built for purpose, whether it's military bases, FEMA, disaster relief or desalination plant or an AI, supercomputer farm or whatever that requires a ton of energy, those kind of things.
Yeah. So what we're doing at the 1 megawatt scale is making a fully portable reactor so that we can build 50 reactors per year. So they come out of a factory and they're all made identical to one another. So no matter which use case you're interested in, right, whether it's, all the ones you just named, it doesn't matter. So it's built for any purpose rather than built for a specific purpose. While all the larger reactors are really these big infrastructure projects. They're going to power fixed assets that you knew about years ahead of time that can wait years for power.
So you're really it's not even in the same market.
That's right.
These aren't even competing with one another.
Right. Yeah. So SMR's a totally different thing from what we're working on is portable nuclear reactors.
Yeah.
And we're making the biggest possible
A lot of
one we can
military
ship.
implications there, which are cool.
Absolutely. Yeah, so it's a...
Because that'll just help the audience understand why that matters. I mean, for our next war, no, I'm just kidding. There's not going to be any more wars. So everything's going to be great. But hate to break it to everyone, but the world is a crazy fucking place. And what we ran into, of course, is you need power, whatever forward operating base you're in. And so to get that power, you have generators. And to get those generators up and running, you have diesel fuel. And that diesel fuel has to be transported on convoys. And those convoys get blown the fuck up a lot. You don't have that problem anymore if you just drop a nuclear reactor down there.
Yep. 5 years of power in a box.
Yep. That seems like a better plan. So how much would one cost?
About $30 million is what it costs. And a lot of that is due to uncertainties in supply chain that we have right now. Once we start building the things, it could improve from
Scaling,
there.
Yeah.
But it's not a massive expenditure and project. And actually, if you're paying $6.50 a gallon diesel today, it's competitive with that without any sort of use of the heat from it, without any sort of climate subsidy. It's just electric power. If you use just electric power.
Yeah.
And you don't bringing a 5,000 gallon diesel fuel truck in every 4 days.
Yeah. It's dangerous.
Yeah.
No, it seems really cool. We're excited. What's for your company like yours? And there's a few companies like this. What is your timeline where you think you guys are actually profitable / making these things? What do Americans have to look forward to?
Well, we're pretty close now. The great thing is we started in 2020, set out a goal of fueling a reactor in 2026.
Okay.
We are on schedule. So we can do a fueled test at Idaho National Laboratory in 2026. We've actually already built up a full-scale unit and did a thermal test. This 22-ton pressure vessel, we did that 3 months ago in our facility in California. We'll be able to deliver a customer unit in 2028 and then scale up from there.
And are these safe for people who are going to be worried about Fukushima or whatever? How am I forgetting the Russia?
Chernobyl.
Chernobyl. Why shouldn't we be worried?
Yeah. Well, the technology is different. There's a couple of factors. So one is the reactor is just extremely small. So there's a really small amount of fuel and material in the system. But it uses a fuel form that's ceramic coated particles. So that every little millimeter sized, every little poppy seed sized kernel of fuel gets overcoated in these layers. And so,
what do you mean by fuel? Do you mean uranium?
Yeah, it's uranium, oxycarbide, 20% enrichment level. The tiny spherical particles are made, right, in this controlled process. They're then overcoated with graphite and silicon carbide. It means that the fuel can handle 1,600 degrees Celsius.
Okay.
Which is like a crazy temperature, right? It's like 2,500 Fahrenheit.
Yeah.
It's unbelievably hot because it's ceramic coated. Normal nuclear fuel that's in any of these reactors you just mentioned, those are water-based reactors, light water reactors. what they do is they use uranium pellets in zirconium metal tubes. Zirconium metal can't handle a very high temperature.
That's what I thought. Yeah.
About 400 or 500 degrees Celsius, it's going to rupture, and then all of the fission gases can come out, and it's a large amount of fuel. So there's a dramatic difference in fuel particle, and it's
Okay, so the ability to withstand higher temperatures means what? Just more efficiency?
it means it can't overheat, it can't melt down. You can't have
I
fuel
see.
melt and start coming down through the reactor, which is what happened to Fukushima.
Okay.
That partial meltdown. Also, a really cool thing with reactor design, if you have a really high temperature limit and you operate down here, as your temperature is rising, the reactor will naturally shut down. So as uranium and graphite in our system heats up, they will actually cause negative reactivity, which will prevent it from being able to go supercritical, which is what happened at Chernobyl.
Yeah.
So that fuel form actually helps you with both of those things.
But some people have died. I mean, how many people have died in America because of nuclear energy?
It's like 1 with an asterisk. It's like a maybe 1 is the answer.
My answer is usually 0.
It's actually, I think it's actually 0, but some people will really argue for that 1. So I think,
Somebody
I'm willing,
slip and fall
I'm willing
in a
to
nuclear
bend.
plant or
I'm willing to
something.
bend on the 1, right?
Yeah.
And
It's important to know. I always bring it up, just like
yeah.
0 people.
Yeah, I mean, a lot more people have died due to commercial aviation, and we're not going to stop flying around.
Yeah.
We're still going to do it. Safe enough.
There's 1,000 ways to die. Nuclear energy generally isn't one of them.
That's right.
What about getting uranium? I mean, one of the things President Trump had talked about in a deal with Ukraine was rights to their uranium deposits. I thought that was pretty interesting.
Yeah.
What is our current situation? There's a lot of consternation about this. Uranium One, Canada. Fill me in.
So we've gotten into the current situation with a pretty lengthy history. As I'll try to just summarize it, but since 2016, we've known that we have advanced reactor developers in the United States that need 20% enriched material. We started to put together funding for that, but delayed it for years, and so funding didn't even really come out for it until last year. And it's about $700 million that are targeted towards having that enrichment capability again. But we've now also invested in low enriched uranium and high enriched uranium.
So what are the percentages of low enriched? What do we mean by low enriched?
Yeah.
What do we mean by high enriched? Because like weapons grade is what, like 90%?
Yeah.
That's what makes those subs so efficient, right? Because they'll use.
It makes the reactor more compact.
Yeah.
But they could use a different enrichment level. I don't think it's necessary, but could use something different. So you got 5% and lower is low enriched uranium.
Yeah.
20% is HALEU and down, right? And then 93% is what you got in a naval reactor.
And a weapons grade.
And
generally.
weapons grade's above that.
Above that even, okay.
It's what you
and
need.
you guys are doing 20%.
That's right. Yep.
Okay.
And at 20%, it's an international commodity. You can move 20% enriched material around anywhere.
That's the legal limit anyway.
Yeah. It's
Well, if you went up to 40%, let's say we made a law that says go up to 40%. Would it really matter for your business?
you'd have to change international law. So it's an international
Well, let's say
atomic
we didn't
energy
give a
agency.
shit. I'm just curious about the technology.
Yeah,
part
it
of
would be material that is closer to a weapon. So if you were to take that 40%, turn it back into a gaseous product, put it in a centrifuge.
No, I understand that.
Closer to a weapon,
I
that's
understand.
all.
I understand why we don't do it.
Yeah.
From a proliferation standpoint, that's not my question. My question is, if you were all of a sudden allowed to do 40% enriched uranium, how does that change your business model? How does it make it? How does that change the efficiency of the reactor? How does it make it more powerful? What does it do? There's a reason that submarines use 93% enriched uranium.
Yeah.
So
it would make our system smaller, right? Or it would make it so that at the same mass. So
because you have less fuel needed because it's highly enriched. Is that why?
Yeah,
I'm trying to just break it down in layman's
you'll
terms.
get more uranium-235 in the same space.
Yeah.
Right. So the reactor will last longer if you keep the size the same, or you could shrink the reactor and still get it to go critical.
So if you keep the same size, you have more power, longer lasting. This is better in every way. The reason we don't do it is because we're worried about proliferation. Is that a reasonable worry? Like, because we'll regulate the shit out of you. We could have security around it. Like, is that a reasonable worry in the modern age?
I think so. I don't think it's necessary to make a massive breakthrough. I don't think it's necessary to change that particular rule for us to make a massive breakthrough.
What rules do we need to change? Why is it so expensive? Why did we build reactors in 4 years before when we had computers that could barely do what a calculator does now? And now it takes 12 years and 5 times the budget. What did we do differently?
Yeah, I think there's a number of things, but it's an excellent point. So way back when we had made naval reactors. Hyman Rickover made the Nautilus. He did that in a really short amount of time. I think it's a 4, maybe 5 year time frame that he did that. Yeah, and you can do everything, literally everything within 6 years. We then decided to make 5 different reactor types, totally different technology types, and do it within 5 years. This is under the Atomic Energy Commission, under Strauss. And we did that. The fastest one was actually 2.5 years in Pennsylvania, a reactor and shipping port. And so we're even faster than that time frame. And those are first of a kind, totally new designs.
This was what years?
This is in the 1954, right after Atoms for Peace is announced under Eisenhower.
It's crazy.
Yeah. So it's totally possible to do it again. And I think what is actually missing is there's only one thing. It's leadership. What needs to happen is nuclear should be a national priority with a really clear outlined goal.
You need a business signal.
You need a
demand.
These many reactors by this date,
signal.
and then just support it.
The market will. But we do have a shit ton more environmental permitting and regulations. There's environmentalist groups that weaponize courts. There's all that. And
that's all. Yep. Yeah.
That's the same with all infrastructure, though. But
Yep.
I ask these questions because we need to solve this in Congress, and this is literally like it's our committee that does it on energy and commerce.
Yeah.
And we've passed some of it. There were some good bills that came through, but
there's been a delegation of authority, right, to these our nuclear institutions, and but I'm interacting with them a whole lot. They all want to help us, but I don't think any of them have clear authority. There's not a goal that they're supporting that they know would run all the way up the chain, right, to the top executives in country, right, so that they know they're doing what is U.S. nuclear policy.
Yeah, and
because all those roadblocks you mentioned,
there's a lot more
environmentalists,
risk aversion than there was before. Too.
Absolutely. So it's a lot of that.
I asked how we got to the moon in 9 years, and I asked an astronaut that, and they're like, by the seat of our fucking pants. That's how, because they just were willing to take risks.
But also because Kennedy said so.
Yeah, we're going to do it, and you're going to take the risks, and we're going to do it. And those are not risks we're willing to take in the modern era, where, we honestly we regulate to near zero casualties. I mean, that's and it's a constant debate up here.
Yeah.
Democrats tend to be much more risk averse when it comes, especially in the regulatory framework, where I'm like, look, just take a little bit more risk and make things more efficient. Now you can always go. That will always be an understandable and debatable tension. In government regulations, but it seems to me in a lot of these cases we've just gone way too far, and so we're always looking to you to tell us like, hey, what if you got rid of this reg and this law? You would have basically no problems. I mean, and you would have a much more efficient process, and you decrease the cost of doing business by $2 billion per reactor. That's the kind of answers we're looking for.
Yep.
So I'd love to hear them. You don't have to tell me off the top of your head, but like from the industry, those we need those badly,
right.
And then we can put that into legislation, and we can make things happen.
Yep. Well, I'm very glad that you're very passionate about it, and we do know a lot of details, but it's minutia we shouldn't cover on a podcast.
No.
There's an example would be, the rules that we're under at the Idaho National Laboratory that we're following are not designed for a company to bring in a reactor that could be commercialized. Mm-hmm. They're designed for the lab to design a reactor.
Yeah.
So we're using a thing not fit for purpose, and that's a law that could be changed or just interpreted the right way. But I think the thing that would majorly help is milestone-based funding programs for everything in nuclear. And all that we'd have to do is add that there's a timeline to accomplish these things by.
Yeah.
So I think a lot of the laws that have passed are putting funding in the right things. It's huge amounts of funding. It's billions of dollars. And there's not actually a strict, by this date, you will have this amount of enrichment capability. That's troubling. That's the thing we need to actually fix.
That's interesting. Yeah, it just allows it to just go on forever without getting any results.
Exactly. And we got to keep continuous competition within these programs, so that there's never like we planned this, now here's the company or companies who've won it, and now that's going to exist for 10 years. Well, what that'll do is block all new innovation for 10 years also. So once you get wind that the government's going to support something and it's hundreds of millions of dollars are going to be given to some company in some effort, you stop, private funding will stop also, right?
Yeah.
Because they'll go, hey, let's find out what the government's doing and backing first. So it can actually have the reverse effect.
Yeah, as a chilling effect. Interesting. Yeah. Well, that's why there is no easy button when we ask these questions.
I think it's an
easy question to ask, but it's the solutions are always a little bit more complicated.
I think there is an easy button, but I'm just maybe I'm like trying to build up the context before I go just push on it, right? But I think if you did what we did for the space industry, which is NASA ran in contract to SpaceX through the Commercial Orbital Transportation Services, which was also won by a few other companies, Kistler, Orbital Sciences, Lockheed, like several of them. That was foundational to creating SpaceX. We wouldn't have been able to get 2 rockets put together and get to the 4th flight of Falcon 1 without that happening.
Yeah. And
that program, supported with $350 million going to SpaceX while they had raised $180 million. That's the kind of funding and ratio there, and it's in a milestone-based program. So SpaceX actually had to build a full rocket stage and go through a pressure test on it, go through a full mission duration firing of rocket engines by a certain date. It had all these strict milestones in it. Was massively successful. So if we were to do that again, we could rekindle our nuclear industry in the same way. So I think that is actually the easy button.
That's an executive decision. I mean, that doesn't really require action from Congress. I mean, I think we should make permitting easier. I think there's the constant debate up here, but what you're describing has nothing to do with Congress. That's just some smart administration on the part of NASA.
Yeah, some funding innovation.
Yeah,
so that there's
need some funding,
milestone-based programs. I think that's a big one.
And that's what's lacking now.
Yeah.
There's some money out there. I know it's funny. Democrats did put some good stuff for nuclear in the IRA, and they never celebrate it. It's interesting. It just goes to show how it's still a stigma for the Democrats. But hats off to them. I hate a lot of the things in the IRA, but they did save a bunch of nuclear plants.
Yep.
And they never brag about it because it's for them. It's still a bad. It's still a third rail in a sense.
They started a little bit. There was something that came out in May. I'll send you a link.
Yeah. No, and we have some other bills and
some mild bragging started to happen.
Maybe
it's
mild bragging. Yeah. Good. I mean, I think we've finally kind of gotten them on board. Because when I got to Congress, it was like, look, let's deal with this climate change debate, and the smartest way to deal with it is not to argue every detail of whether human caused climate change is happening or not. There's certainly a debate to be had there, but if we're just being real, the politics of it are that most people are convinced that there is a disastrous effect from human activity on Earth. Okay, so maybe our best bet is to move past that, move on to solutions, and that's where you actually start to beat the crap out of the radical left environmentalists because they want crazy solutions where the math just doesn't work. And we've discussed that briefly before, where you're putting intermittent energy sources on an electrical grid in an environment where you're going to have 50% larger energy demand worldwide in the next 50 years, and the math just doesn't work. So you need reliable energy. And look, hey, we want it to be clean. I'm with you. I want it to be clean.
Yeah.
So move past the argument is what I tell and we have as Republicans, we've done a decent job of that for the most part. And it's pushed Democrats into an impossible corner. They can't defend the absurd subsidies for solar and wind. In fact, the more data we see, the more it seems like these aren't even really on net carbon footprint, not even really much cleaner.
Yeah. One of the really cool things about the scale of plant we're building is that it actually works really well with solar or wind to back up those sources so that if you've got weather or just nighttime, you don't need huge batteries.
Turns out the sun leaves.
Yeah.
It leaves every day. So unless you're in the summer in the North.
Yeah, unless you're high up enough in space.
Yeah.
Out of Earth orbit.
Yeah.
But it turns out you can have a solar plant that's designed to be 5 megawatts or up to 20 or 30 megawatts. You can leave a little carved out area in that and have our nuclear reactors in it, just inside of that plant. And now you have a reliable source that's going to catch some sunlight during the daytime just to help with costs a little bit.
Yeah.
It makes the life of the reactor go longer, and then you have an extremely resilient power supply out there.
Yeah.
Where it's not necessary to have battery minerals come out of the ground, right, with questionable human rights conditions.
Yeah. And to be fair, from my just kind of taking a step back, problem solving perspective, my first question would be why don't we just have the nuclear plant? As opposed to just having, you know what I mean?
Yeah. It's like if you've got the land, you can augment it to get the cost down.
If it's already there, for sure, leave it there.
I'm just an engineering purist, so I'm there's a spreadsheet for every exact energy market where you can dictate, here's exactly how much of each power source is the best. Right?
Yeah. No,
I'm just making a new possibility.
We should think that way because, I mean, I would argue that there is an upper limit to, how much of, say, wind or solar should be the energy mix of any particular electrical grid. And, in Texas, it's like 30%.
Yep.
That's a lot. Because if that all goes offline, like it did, in the past,
yeah.
Well, you better have a way to ramp up natural gas plants really, really fast. And maybe they were down for maintenance because it's winter, and maybe some shit froze, and then we were where we were. Real quick, you got to go soon. I don't know if this is within your portfolio at all, but some interesting advancements on fusion. In recent time, what do you think? Is that what do we think about that?
I have no idea. I'm like not qualified to comment. It's
Okay.
like that's the best position. I hope fusion works. I think if it does, it'll probably be really large, and so I don't really think about it much because I'm like, it probably doesn't affect the portable nuclear micro-reactor market too much. I think one of the things we haven't talked about is our ability to put power out in a really forward situation. So we have all these areas in Alaska where there's like 150 microgrids in Alaska where they're using almost 99% of the time it's diesel fuel. So, and it's their only option. It's because they've got permafrost. They don't have big areas where they can put up solar panels or clear off all the snow landing on them.
Nope.
And so they can't use it. And in these really remote regions, we're kind of the only option. And if you look at the energy costs, there are subsidized energy costs where they're paying like over $1 a kilowatt hour in a huge number of areas. And you got similar places like that in Canada. You've got remote military bases like Thule Air Force Base in Greenland, where this kind of power source is the only option.
Yeah.
And then if you extend that to space
Well, now Trump's coming back. We might buy Greenland.
yeah. We offered once.
It wasn't the craziest. He got made fun of so much. It's not the craziest idea.
Yeah. I mean, we have a major Air Force base up there, and there's assets we need operating over there. But space is just the most forward operating base that there is. And so if you look at that energy mix, like what you need in a location, you need more and more nuclear. The more in those tough areas you get on Earth. If you're high up in mountains that are snowy all the time, or you're way up north, you're going to need more of it, and it needs to be smaller. You need radiant Kaleidos nuclear reactors.
What's the smallest you have right now?
Well, we only have one product, so we're only making a 1 megawatt electric generator, right? So to replace a diesel generator.
Yeah.
Right.
How big is this?
It fits on a truck.
Okay.
Weighs 70 tons.
Is it about like, if you think about like a cargo container, is about like that, more or less?
It's a custom package because it's got to handle all the transport loads and support a reactor, right, and shielding surrounding it. So
can you put it into a C-130?
You can't, but you can put it in a C-17.
Okay.
C-130 is a little light. I think it's 20-ton lighter payload capacity.
Gotcha. But you can put it in a big plane.
Absolutely, yeah, and that's the target. So you can put it anywhere you want, and in those extremely forward locations, it's your only power source. One of the really cool things you can do with it too is you can deliver this power source the last 5 years in just a couple of days. So a lot of companies have challenges, right? They want to do something, they want to build something, they want to deliver something of value to society, and often they can't do it. They'll go to their utility, and the utility will go like, get in line. It'll take you years before we can add that amount of power or capacity. So what we're finding our customers, data centers, mining companies, oil and gas companies coming to us and going, we like the speed of this. We like the ability to instantly go bang, like let's patch an extra megawatt or an extra 4 megawatts wherever they like, whenever they like. Yeah.
Even in just big cities, just as backup power, there's a ton of.
And this is the only way to do it. I mean, if you in a big city wanted to add 4 megawatt of any sort of combustion based energy, you're going to have 4 megawatts of exhaust fumes also, and they're just a nuisance. And there's a way we can do it with nuclear. Yeah,
that's very cool. And I already asked the question, but maybe repeat it. What's the timeline you think you guys are actually selling this stuff?
2028, first unit to a customer. Ideally, that's a military base that has very great need, that would make great use of this. We'll then have 3 units the next year, 8 the next year, ramping on up to 50 a year by 2034. We'll be able to work on space reactors also.
Yeah.
Coming up. For now, we're extremely focused on the 1 megawatt scale.
Then you got to get one to the moon and then to Mars.
Yeah, 1 per week to those locations, maybe.
Yeah, no problem.
Mass production, something that's lasting and has a huge impact. And I do think we could announce a really high level goal for our country for nuclear. And in space, really recently, Russia and China announced working together on putting a 500 kilowatt reactor on the moon.
What do you think their chances are of actually doing that?
Russia knows how to make reactors. They've launched way more space reactors than the U.S. has. We've put one in space in the 1960s. And so they can probably do it, and I think China can get it there and land it. So we should take it seriously.
Yeah, that would be a blow to American ego.
I think we should be first.
Yeah.
And that could go a long way as a call to action.
Yeah, well, that's a good goal to have, and certainly don't want them there. Then you're back in the Netflix show Space Force, battling the Chinese on the surface of the moon.
Yeah,
underrated comedy show. Doug, thanks for being on. I appreciate it.
Yeah, thanks for having me on.
Yeah, of course.